title of the talk is Microwave Micro Machine Integrated Circuits. And this morning now you know that I'm a professor at IIT, but because of lack of time I didn't say I have in IIT now last 27 years. I joined in IIT 27 years back. My specialization is radio frequency in IC design, and 4 or 5 years back we decided that there's a new area which is opening up. It's called RF MEMS, radio frequency MEMS. So we decided that why not we now change, as I said in the morning, you have to be a reconfigurable teacher. Why not change from the conventional RF to the micro machined circuits? And we have been able to complete 14 major projects in this area with a deliverable from each project. And whatever I'm going to present to you here is made in India, made in Delhi. I take about 10-15 students from outside of IIT. You want to come down and spend some time with us, you can come down. Indian National Academy of Engineering, INAE, has a teacher mentoring program. A fellow of INAE can support 2 teachers. I am a fellow, so I can support 2 of you. You will get money from INAE and I'll also get some money. So you can spend 2 months with me doing research at IIT. So please make use of it, INAE. And first come, first serve, we can take every year 2 students. So with these, we will go ahead with the presentation. Now the talk is Microwave Micro Machine Integrated Circuits. When I use microwave, it includes RF, it includes millimeter wave, it includes sub-millimeter wave. It's a broad topic. First, what is micro machining? Now, micro machining is broadly defined as a selective removal of silicon. I put here silicon, but it's not true. We can use many dielectrics, but silicon is most popular, to result in suspended structures as membranes. So we are basically trying to create some circuits which we do on PCB, normal PCB, on a membrane. We remove material underneath the PCB. That's the whole technology here. The technique is called bulk micro machining. So if you see this view graph here, we have silicon, which is 100, and we deposit silicon dioxide, silicon nitride using standard sputtering techniques. Then we can put this substrate into a solution KOH. People say that we need $50,000, $80,000. You don't need that. A simple petri dish where you can have KOH, and we can have selective removal of silicon. And important thing is we can create a structure like this. This is very important for me. I can remove selectively some material underneath the conductor which is given here. So this process is called bulk micro machining and extremely useful for building high performance antennas, high performance microwave circuits at high frequencies. Very easy. Then another technique is called surface micro machining. So when you are interested in developing a switch, that means you have a beam which you would like to move up and down, so we use surface micro machining. Here substrate is just used as a support. We don't play with the substrate. On top of it we deposit some layers which is called an isolation layer, then a photoresist which is called a sacrificial layer. Then we pattern this layer and create a groove something like this, and then deposit gold, and we have a metallic layer like this. Then we remove this dielectric and we have a hanging structure which is called basically a cantilever. This is a singly supported cantilever. For most of the RF work we need doubly supported cantilever. Then we have another technique called Liga technique, but which I am not describing here. That's not much used for microwave work. So we'll be stressing mostly on bulk as well as surface micro machining. Why micro machining at microwave frequency? We have PCB techniques, we have circuits reported up to 140 gigahertz without micro machining. Why should we go in for micro machining? I've taken an example of an antenna. Let's look at this structure. Is a simple PCB. It's called microstrip. It's a dielectric substrate. On top of it, we have the metallic pattern on top of it. And if you look at an antenna structure, we have a patch, which is very wide patch. Then we have a transformer. Then we have feed line. If we put electromagnetic energy through a connector here, this patch radiator properly designed will radiate in free space. Now the radiation will depend on what kind of material you are using. Now if we are thinking of micro machining application, we will use a silicon substrate. Silicon has a dielectric constant which is around 11.7. Now the moment I use 11.7, its tan delta is very poor compared with the microwave dielectrics. Resistivity is of the order of 10 to the power 3 to 10 to the power 5. It will result in very high losses, and bandwidth for an antenna will be considerably shrunk. We have surface waves. These are the electromagnetic waves which propagate over the dielectric substrate, which will result in degraded radiation efficiency because the field is bound to the dielectric because it's a high dielectric constant material. So if we use silicon, I cannot use this antenna effectively. It has a lot of problem. So what I'm trying to do, I'm trying to create a small air gap between the metal plate and the dielectric. A very small air gap. Now this air gap cannot be milled using conventional machine because the air gap is of the order of 100 microns. Accurate 100 micron air gap is needed. So it is here where I use bulk micro machining to create the air gap. So what I do, I use the silicon, create a bulk micro machine cavity underneath, and then leave some silicon here. On top I can have silicon dioxide, silicon nitride, many materials can be deposited. Then we have conductor. If I do this small modification, that is create an air gap to the conventional PCB thing, I get lot of advantages. Very low loss, no surface wave, higher radiation efficiency because it's now more or less like an air structure. Less dispersion, nothing changes with frequency, extremely high bandwidth, less sensitivity. If the dielectric constant changes here, it will be less sensitive. For example, if I take the circuit to Leh, I take the circuit to Rajasthan, temperature differential is 50 degrees. So 50 degrees dielectric constant will change because it is temperature sensitive. So here you will see resonant frequency slightly offset. But here resonant frequency will not be offset because it is an air medium. So this is one of the advantages. Bulk micro machining can be used to realize high performance circuits. The second one is a switching application. So you have a microwave signal, you would like to route it to this circuit or do this circuit, is done by a switch. Now switch can be created using surface micro machining. You can have a quartz substrate or silicon substrate. Then as I showed earlier, we deposit several layers. And I have a conductor here, I have a conductor here, conductor here. This geometry is called coplanar waveguide. On top of it, I deposit a silicon nitride dielectric and then create anchors and create this membrane. The G0 is of the order of 2 microns, 2 to 3 microns. It's a very, very small air gap which is created using surface micro machining. So once I have a structure like this, I apply a DC bias voltage between this conductor and the outer, which is a ground conductor. When no voltage is applied, so nothing happens to the membrane, we get some capacitance C0, and we can design it in such a way that the microwave energy is passed onto this conductor. We will have this coplanar waveguide act as a perfect microwave transmission line without any loss. Now the moment I apply a bias, typically 60 to 80 volts, but now it is reduced to about 5 volts, negligible current, I am actually applying a force between this conductor and this conductor, and depending on the magnitude of the voltage, I can collapse this bridge. When I collapse this bridge, that means we have very large capacitance because one conductor, another conductor and a dielectric here. So it forms large capacitance. So depending on the design, I can cut off the microwave power. So in one case, power is transmitted to the other end, one case there is no power. So this is a very, very important application. Now advantage of this kind of switch over conventional gallium arsenide and pin diode switches is extremely low power requirement, microjoules. Low insertion loss 0.02 to 0.2 dB even at 30 gigahertz, very extremely low loss. High linearity because this is not an active device, it's a passive device. And compact design, dimensions are of the order of micrometers or nanometers depending on the frequency. So the wave graph here shows the first made in India gallium arsenide switch. Very few papers in the literature are available. This is done by a PhD student at GATEC. So you can see this is a coplanar conductor, center conductor, outer conductors. These are these two ground pads. And then we have this black pole, the silicon nitride here. And then on top of it, these are the two anchors. And this is the membrane which is perforated. So we have tested this, this works. We have given about 50 designs. This is one of the designs which is made in India. By April, we are trying to complete this project. Each wafer processing is about 20–30,000 US dollars. Each wafer processing, we can get about 1,000 switches from one wafer. So that's the kind of complexity, but it's a very, very complex process, not as simple as I'm showing you. A lot of simulation work needs to be done before we can go. So this is another important application why we should switch over to micro machining. As a comparison between FET, pin diode and the MEMS electrostatic switch, I have given a table here. This is voltage, current, power consumption, switching time, cutoff frequency, power handling, loss, isolation, and the series resistance, which is a very, very important parameter for cutoff frequency. If you look at FET, voltage requirement is 3 to 5, MEMS 20 to 80. With a charge pump, I can go to 5 volts. So voltage is not an issue. Current is practically negligible between FETs, but pin diode requires a large current. Power consumption 0.05 to 0.1 is the lowest, similar to FET but it's a non-linear device. Cutoff frequency is the highest. It's about 80 terahertz in some of the switches. Power handling of the same model is slightly lower than the other two, and loss very, very low, extremely low loss, isolation high, and we have RS series resistance very, very low. If you're thinking of using a system where you have 100 switches, you see the loss. Loss plays a very, very important role. So it is here where RF MEMS switches will be very, very important, and I think worldwide thousands of billions of dollars are right now going on in research into the RF MEMS area. It's a very, very hot topic. We have very few papers on gallium arsenide switches. Very few papers. In fact, I've seen only one of the papers on an actual switch at X-band, nothing beyond that. So it's a very hot topic to work on. Then third important thing is, why micromachining again? Tunable circuits. I want a filter to be made. In the conventional PCB, I can make a filter, that's it. I want to tune it at 10 gigahertz. Now I apply a bias, same filter should work at different frequencies. So I can do it here using MEMS. So if you look at in the switch application, I collapse it totally. For the tunability operation, what I do, I create a structure which is called an end couple filter. I have a microstrip conductor gap, microstrip conductor gap, microstrip conductor. I can design it using standard textbooks, make a filter. So the filter response will be like this. This is a band pass filter response. About 15 gigahertz is the center frequency. Now, I don't do anything. I want to apply a bias to this filter and change the frequency. So what I can do, I have these bridges. Each one is a cantilever double bridge over each resonator. Now I apply bias to these cantilever bridges. I can partially move it, not collapse it, move it. So what is happening? Capacitance changes. When capacitance changes, resonant frequency, see, we have air gap is 2.8 micron. I reduce it to 2, 1.5, 1.5. Resonant frequency changes from 15 gigahertz down to 11 gigahertz. So it's a tunable filter. If I have a received signal which is 10 gigahertz, I tune it by applying voltage so that it becomes smaller, air gap. Like that, you know, I can get tunability into this one. 23,900. So this is another important application. Same circuit can work at different frequencies by simply controlling voltage through a computer. I can control and make it work at different frequencies. Then important circuit, reconfigurable. Now can I make the low pass filter which gives cutoff frequency 10 gigahertz? Very easy to design on a PCB. The low pass filter prototype is a capacitor, inductor, capacitor, inductor. I can choose these values from standard textbook, Mathai's handbook. I can design LC. Connect these LCs, I have a low pass filter, but with fixed cutoff frequency. But I can realize these also using transmission lines, and again I will have a fixed cutoff frequency. But idea here is, can I make a reconfigurable filter? Question is yes. How you can make it? Look at it, what we do. I switch down these two capacitors. These capacitors I realize using the bridges. Now I apply bias, I switch them. So these capacitors are effectively large capacitances because there is a silicon nitride there. So if I do that, this is the second case. What I do, I short these three and leave those two open. So if I do that, I can get the following. Only lump components are used, very compact design. Tuning ratio depends on number of placement of switches. The tuned frequencies can be digitally controlled, and we can have very low loss because quality factors of these micro machine inductors could be very, very high. So this is what it will look like. These are the capacitors, 5 capacitors. Now if I apply a bias to these two and switch them off, now I'm getting this characteristics. I'm getting a cutoff frequency of 10 gigahertz. So I can pass 0 to 10 gigahertz signal, rest of it will be heavily attenuated. Now I digitally control now the other three and release those two. Now these three are down, so I go down, I get my cutoff frequency 30 gigahertz. Filter is same, except that I am applying a small bias voltage to switch the capacitors on and off. So this is another important advantage which I don't have in the conventional microwave circuits. Once I make a low pass filter, fixed 10 gigahertz, 5 gigahertz, 30 gigahertz. Here I can make a reconfigurable circuit. So this is another important advantage. Then this kind of thing will be very useful for electronically scanned antenna, because each electronically scanned antenna, that is, antenna is fixed, but I am moving the beam electronically. So in each system will have at least 5 to 10,000 phase shifters. 5 to 10,000 phase shift is a large number. So if you look at frequency X band, Ka band, V band, W band, these are basically 10 gigahertz, 35 gigahertz center frequency, 60 gigahertz center frequency, 94 gigahertz center frequency. Now the architecture of the array will be, we have a power coming, microwave power, I have phase shifters which are variable phase shifters in each branch, then I have receive or transmit receive module. Each transmit receive module is 2 lakh rupees, 4,000. Think of $1 billion, not a 10 rupee kind of scenario. So we want to save 1 TR module, we save 3 lakh rupees. Then I put radiating elements which are in the 2D space, basically a planar array. So I feed microwave power, I can change the phase shift of these phase shifters and get the beam changed in the azimuth elevation. But if you look at the typical gallium arsenide FET switches, I get -3 to -4 dB loss at 10 gigahertz, -6 to 735, -8 to -9, 60, 9 to 10 dB loss, 94 gigahertz. This is a very heavy loss. This is the state of the art. Now, if you look at this kind of loss, what will happen? You're putting a phase shifter here, it gives me 10 dB loss. A lot of power is getting lost here. Then I need a TR module. I amplify it, use a power amplifier before I transmit. So architecture becomes very complicated. Now, if I go to MEMS switches based phase shifter, I get here 3 to 4 is 0.9 to 1, a reduction of 3 to 4. 9 to 11 becomes 2.7 to 3.3. So significant improvement loss and linearity because these are non-nonlinear devices. So I can change my array architecture to have 1 TR module to feed multiple phase shifters because losses are very low. Similarly, so this way I can reduce large number of TR modules, so the array cost will considerably come down. These are, if you look at the website on DARPA Defense, these are the current projects which are on and very important because you save billions of dollars from one system. So it's very important area. Now looking at commercial people, because most of the times, we have problem in industry. Industry wants quick solution and a commercial product. Look at handset now. You have mobile handset. If you want to add one function, for example, you want to add another protocol, you need at least 10 millimeter by 10 millimeter additional space for building that circuit. Now here we have different protocols, UMTS, GMS, DCS, GSM, DCS. So like Motorola phone uses quad radio. It can take 4 bands. It has 4 different radios which take the bands. But I need 10 different radios, 10 different protocols. I cannot increase the size. It is very, very expensive. So what is done? This entire radio is made reconfigurable. So what you do with multiple switches, I can tune the frequencies of the circuit as I showed you filter, so that the same radio receives UMTS, receives GSM, receives DCS, like that. So this reconfigurable system is currently being worked out at Nokia, Motorola. So you will have future mobile phones using the RF MEMS technology because of reconfiguration. Size remaining same, additional functionalities will be incorporated into the system without affecting the cost. So it has tremendous commercial application. Then another important thing is power combining using active antennas. So what's happening as you go higher and higher up in frequency, getting a source of microwave power is difficult. Millimeter waves, you cannot generate more than few milliwatts, very, very expensive. So what is done, we don't generate power, we use an integrated oscillator with a radiator called an active antenna. So this is an radiator, come oscillator, radiator come oscillator, and we use locking signal to have all of them give the same phase so that I can have beam in the broadside direction. I can phase them so that I can move beam in the azimuth elevation. So we are doing space power combining rather than building very sophisticated oscillators. So this is another very important area which is currently being pursued. So these are some of the advantages. You get high performance antennas, reconfigurable antenna array, compact multifunction wireless communication systems, power combining using array of active antennas, low cost, less weight satellites, microsatellites, low loss, low power switches and phase shifters. Then we can have affordable millimeter wave systems. They're very expensive today. Integration with CMOS electronics and MMICs. So these are the advantages of the micro machine circuits. Now what all we need to do and design such circuits? This nice theory. The first point is most important. That's why I put it red. Willpower and sincerity. I will do it. This is what we took 3 years back the decision. I don't know MEMS. I don't know micro machining. We said our group will produce made in India MEMS first time. So we embarked on a very ambitious program. And we have almost 5-6 crores funding and done pretty good. I'll show you some of the results. So once you have this willpower and sincerity and good students, everything is done by students. Then we have to select a suitable transmission medium and substrate. Silicon, gallium arsenide, quartz, what do you want? you have to go systematically. Development of transitions, because you have to launch electromagnetic energy. Passive component development, filters, inductive circuits, band pass filters, reconfigurable circuits, antennas, antenna array, active antenna, switches, phase shifters. Then you can think of integrating everything. You have real technology. You're not borrowing technology. You have your CAD programs, your models, everything you have to do. Because this thing is not available even if you pay millions of dollars today. You cannot get a switch technology from anywhere in there because it has military applications. So we decided, many groups now in India are working in this particular area. But this, you remember, is most important. This, if you want to venture into this area, you can do it with pure simulation tools today and link with a foundry like SCL. They can make circuits. In fact, I do work with SCL. I'll show you one of the very nice circuits. First time in the world they have done. I have the picture of it. It's an array, 64 by 64 element. Could do it just next door to your thing. But the crux of the thing was design. Let's see how we do. We start with theoretical analysis, which all your students can do. Say, when we take a silicon substrate, print the metallic conductor, we use any structure simulator, generate frequency versus number of modes it supports. As I said, if you don't use bulk micro machining, we have many modes. You can see one mode, two modes, three modes is not acceptable. So we have to have a transmission line which will only have dominant mode propagating. So that's the first thing what we need to do. So then we introduce a bulk micro machine cavity. We can create a bulk micro machine cavity. We can also mount this entire circuit on glass and then analyze this. When you do the analysis of this, you find very interesting results. From 10 to 40, we have only one mode. So we have eliminated all higher order modes by creating bulk micro machine cavity. So theoretical analysis is very, very, very important. The next thing is, we have done theoretical analysis. Now I have an option of keeping it in my pocket or sharing with all of you. So we decided we will share with you. How to share with you? Because these tools are costing 50 lakh rupees. You can't afford it anywhere. So we decided, put a student on this job, develop closed form expression which can be used on a calculator. So we took a very generic structure which is very complicated. Metallization here, metallization here, metallization here. All possible permutation combination, and then finally spend 1 year to develop these expressions. These are already published. Effective dielectric constant of this very complicated structure is a very big thing. You can program it in MATLAB in 5 minutes. Then another important parameter is impedance. And impedance we are given a very close form of 29.6 pi square root E effective, 1 plus natural log 2, 1 plus root k by 1 minus root k. So you can generate now this design data. You need not repeat the exercise. So today you can have a transmission line, generate data in 1 minute. Once you have done this, then we also have to check what kind of silicon we choose. Should it have resistivity of 1 ohm, which is normally the thing, 100, 10,000. So we ran attenuation versus frequency. We found if you use resistivity 5,000 ohm, 1,000 ohm, 100 ohm. No, 100 is here, 1,000, 5,000. So the loss depends on resistivity of the silicon. So we have to go in greater than 5,000 ohm. We use 8,000 at IIT. So this is very important. Otherwise you take silicon and print it, 20 dB loss is of no use. So this is another important parameter. Once you do this, then you start with low pass filter design. Now it's a very interesting, in fact it's just published. It's really very recent work. If you look at microstrip low pass filter, this is a inductor, this is a capacitor, inductor, capacitor, inductor, capacitor, inductor. But that's the conventional PCB design. Now what happens in this design, if you want to make a perfect inductor, its impedance should be very, very high. On a conventional PCB, impedance achieved is 100 ohms. It's not a perfect inductor. So what we did, under each inductor on the back side, we cut out a micro machine cavity, make it bulk micro machine. So the impedance of this line becomes 200 ohms, which is a very, very good inductive line. So we made several such circuits. We made this entire thing on one cavity. We made these inductive lines on 3 different cavities. K connectors on both the sides, and this is the test jig. So these are the bulk micro machine air cavities created under these 3 under the inductive sections. Here it is one bulk micro machine cavity for the entire structure. Both work. You have to do a lot of modeling for these. The second thing what you have to do, we deposit silicon dioxide sputtered, or you deposit silicon nitride. Now which one is better? So when we have to cut make 8 millimeter long membrane, chances are that it may sag. So this is what happens actually. If you use silicon dioxide, it is 8 to 10 micron buckling. If you use silicon nitride, the buckling is 0.8 micron. So this is quite stable and rigid. In fact, now we are using combination of silicon dioxide, silicon nitride. We found it is very, very rigid and long term. So these studies need to be done to establish what kind of membrane structure or the layered structure one has to do. Once you do that, the filters work. This is a type 1 filter, and this is your simulated and measured results. They are perfectly okay by any standard. And the type 2 measurement is also shown. In one of them, you see that the stop band is better than 20 dB, and here theoretically it is supposed to be much better, but practically we get a resonance here. But they work. So low pass filter with very, very low insertion losses can be made very easy. Then the second thing we tried, why not make a band stop filter and see, because we have to make each component and see and combine the library to make the system. A band pass filter is called a spur line filter. We can cut a couple line here, and this portion is over a cavity. There's a metallic, there's a bulk micro machine cavity underneath, and this is a microstrip line. So this is the cross section. It's the air cavity membrane, and then we have silicon nitride or silicon dioxide. 270 micron wafer, 3 micron dielectric membrane thickness. These are various transmission line optimized. So printed it, and let us see what happens. So this is the front side, and this is the big cavity which we created at the back side. You see, very interesting result. If we don't create this cavity, no cavity, then we have a attenuation, stop band attenuation of 22 dB. The moment I create a cavity, I get minus 45 dB, 20 dB improvement by making a cavity, and this is highly repeatable. You can see all the three center frequencies are perfectly okay. There is no deviation, and this is not the 10th filter. This is the first filter which the PhD student made. It's highly repeatable if you do your theoretical analysis correct. But this is also published in very recently in the Sensor Letters of September 2007, the 7-page paper. This is not very old technology, very current in our group. Now we create this double spur line structure, and I attach a switch here, a cantilever switch. Now if I put switch off, that means both these lines are as such. The switch doesn't do anything, so I get a resonance at about 8.5 gigahertz stop band. Unfortunately, this slide in my thing is okay, but it's not coming okay. When I put this switch on, that means one branch has length L, another branch has length L by 2. Now you see this center frequency shifts to 15 gigahertz. That means I can have a tunable band stop filter done. So this is another important advantage of using the MEMS structures. Now let us look at antenna, which is one of the very complicated designs. If you look at an antenna, patch antenna, you see this dotted line is a cavity underneath the patch. Now this is my feed line, which is on bulk silicon, and this portion from here to here, if you look at cross section, this is the feed line. The substrate also tapers. So the material on top is partly on the bulk silicon and partly on tapered dielectric, which is very complicated to model. So this is the most important thing, is the modeling of this structure. So we need to develop a transition from bulk silicon, which is basically this, to air cavity structure, which is here. But in between this, we have a 54.7 degree taper in the dielectric, and the conductor runs all through this. So to design this and optimize it. If you print it straight away, it won't work. So we have to design it if you want the antenna to work. So this is how we do, the students do the simulation on structure simulator. And then this is the first fabricated transition back to back. This is input, this is output, and this is the bulk micro machine cavity transition. And we did several of them, about 100 of them we made. You can see the transmission loss and return loss of them. Is 2 transitions with 10 centimeter line, 10 millimeter line is less than 1 dB. It's about 0.3 dB per transition at 35 gigahertz, and return loss better than 15 dB. So we tested on wafer level many of the transitions. That means the design is okay, transition works well. Once the transition works well, next thing is to make the antenna. First what we did, we used time control etching. Basically we put the silicon on in KOH and noted the time approximately, so that few microns of silicon are left. So we have basically air cavity, 4 to 5 microns of silicon, and then we have the radiating patch here. So we did this design. So this is a standard formula, frequency 35 gigahertz, radiating patch ground height is 270, effective dielectric constant 1.45, and then found the patch dimensions, 3.5 by 3.5, designed the transformer, and then designed the feed line. So we calculate the input impedance, comes 143, the transformer impedance comes 84.73. So once we do this, we make a mask. So this is the front side mask, where the conductor pattern is to be printed, and these are the bulk micro machine cavities underneath. So we have to have two sets of mask, and this is the first fabricated antenna in India. We did it at 35 gigahertz. You see, this is how it is mounted in the test jig. This is a K connector, and this is the patch, and this is glued to the brass housing. When you flip this substrate, we have a bulk micro machine cavity, and this membrane is on 5 micron silicon, only 5 micron silicon. So when you test this, this is the test result. Resonant frequency, we had simulated 34.5, measured 34.2. It's not bad, first attempt. And all other parameters are better than what we simulated. So, but when you go to an industry, they say 34.5 and 34.2 is a large difference, because they need 100 antennas at 35 means 35. So we spend, in fact, the PhD students spend almost a year to find out what is the reason. So what we found, when we dip different substrates into KOH, you cannot control the time so accurately, so H rates are different. So 1 second more means it has removed half a micron more. So that's the reason. So what we did, we deposited silicon dioxide, later we deposited silicon nitride. So this acts as almost like a H stop. So when we put this in KOH, after it reaches here, it temporarily stops. So it can go through silicon nitride, but its H rate in silicon dioxide is slow. So we are able to control to exactly 2 to 3 micron of silicon dioxide. So this process is much better from production than theory. So we did a lot of antennas now. The second thing what we did, if this antenna, this L and W are 3.5 millimeter, and then we have a cavity of a particular dimension, if this is offset, it also makes a difference. So we did all studies, offset, feed offset, and finally arrived at what are the important parameters which control the resonant frequency of this thing. So this is the front side, and this is the back side of this new antenna developed at 36, and this is how we mount it on the K connector. And you see now there's no deviation. 36 is 36, and you have bandwidth roughly about a gigahertz coming very easily, while the VSWR is less than 2. Then we had E-plane, H-plane pattern measurements, fairly okay. Then we went into several types of designs. So we made a coplanar patch. This is again another types of uniplanar patch, triangular design, circular one. Each one is 3 to 4 month job. And all these antennas are published in the literature. Some of them are coming in June of international journals. So these are the back sides of these antennas. Now this membrane here is silicon nitride, silicon dioxide sandwich. We found that is the best as far as the buckling is concerned. And all these antennas have been tested several times. And you see, this is a circular patch antenna. You see simulated and measured results. Perfect now. This is a triangular antenna. Simulated measured results are perfect. I'm showing you only return loss. I'm not showing you pattern because we don't have much time. So we developed confidence that these antennas can now be made here. But again, when you go to defense, they say, you made one antenna. We need arrays. Single antenna is of no use. So we ventured into making arrays. They are right, because single antenna is not useful really for communication, because we would like to have a beam which is narrow, we would like to have gain which is increased. Now we have the patch designs ready with us. Another thing is we have to now design power division, very complex power division network. Cavities will be created under these 4 patches. So we did a 2 by 2 array first, because limitation was 2-inch substrate. We were initially using 2-inch dia substrates. Now this is the first 2 by 2 array made. These are 4 cavities, and this is the pattern on top of it. You can see the theory and experiment matched very well, because the simulation results are quite okay. So once we did this, again these people came back, no, 2 by 2 is of no use. We need minimum 64 elements. So now comes the problem. Now we have to make a 64 element. Now the size of the wafer is 6 inches. IIT Delhi doesn't have 6-inch wafer processing facility. SCL has 4-inch. So we finally optimized it to fit in 4 inches. So 64 element, very complicated power division network. And then we have under each antenna there is a cavity on the back side. And the patch rests on 4 micron silicon. It is a very, very complicated process. Now, our major problem is that I have put a dotted line here and a dotted line here. I'll explain to what these are. Our major problem came the following. The membrane thickness in the micro machine area is 10 micron. It sits on 10 micron patch. The wafer thickness is approximately 700 micron. Where electromagnetically we have to have wafer thickness only 270. Now there is no machining possible. So what to do? It took us almost a year with the SCL team. They were very nice, very kind. And we worked out a process. See the process. 680 micron wafer, we do that big dot I showed you. We do a bulk micro machine big cavity. So basically remove entire metal material here, big micro machine cavity. Once we do that, that means we have scooped off most of the material chemically. Then we are now at this level. Then under each patch, we do a localized 64 element cavities. So leaving 10 micron for the array. So this is very complex. It took quite a bit of time, and finally this is the array. This is a production array. We made several of them. It's a front side, and then this is a circular wafer. We cut down and make it a square wafer. So these are 64 elements, several power division networks, feed line, and back side 64 perfectly aligned. 0.2, 0.3 millimeter is the only overlap region of this thing, and very thin one. We can cascade several of them to make bigger arrays. We can't go bigger than this because our process is limited by 4-inch wafer. So this could be done, and this is the result which is done in Feb 2006. Is 35 gigahertz antenna array is done. Now if we have to do active antenna, so what we have to do, we have this patch is already done. It's a 2-port patch. So we would like this patch to radiate some of the power. Some of the power would like to feed back to a amplifier circuit, which is an HEMT, and then satisfy. We have the phase difference equal to 2 pi, Parkinson's criteria we use, so that this circuit oscillates and also radiates. So we attempted this, quite complicated. So first we have to do the 2-port patch design, then do matching network, design an amplifier here, and have the feedback path so that it works. The configuration has been used, not in the MEMS. Simple, not strongly dependent on amplifier characteristics. If the gain reduces by a couple of dBs, doesn't make a difference. 2-port patch has to be properly designed because we don't want everything to be radiated. Part of it to be radiated, part of it to come back. So we used a MMIC LNA chip, then created a bulk micro machine cavity under the patch, another cavity here so that we could mount the MMIC chip, and we created these extra because the process is so complicated we can't do any tuning. So we created U-shape because the total phase has to be 2 pi, integral of 2 pi. So we created 2 U cavities. In case it doesn't work, I can put bond wires here and do some tuning. So we did this, and this is the circuit which is fabricated, quite complicated. And this is a place where we have to fit in an amplifier. It's a through cavity created using bulk micro machine, place for capacitors for the DC bias. So this was assembled. So on the brass housing, we have to create a bump. One of the problems was wafer was 270, MMIC chip was 100. 170 micron difference in the height will create problem. So we raised a bump of 170 microns so that we could put the chip at appropriate place so that the bonding is very, very easy. So these are some technological issues, and this is how the final complete active antenna circuit was done. This is, in my opinion, first active antenna circuit developed, and this is already published in IEEE. This is the response. The frequency was designed at 35, shifted to 35.6. Power output is low. Now this was a very old design, and we did a systematic analysis to improve the power of this particular chip. So it's possible to now design different types of circuits using the technique which I have described. Now the most important thing is, if you make an array of these active antennas, we have to have an injection locking circuit. So each circuit has a bias so that this works as an oscillator. Unfortunately, the tolerances are such, this will work at F1, this will work at F2, this will work at F3, this will work at F4. So if you don't take care of dimensional tolerances and use injection locking, so we made a test board of it, and you see this is what will happen. So the spectrum will be of the oscillator will be like this. It's not at all an oscillator because each radiator oscillates at different frequency. Now this injection locking mechanism is very, very important, and we did a lot of theoretical work to see whether we can predict why to feed injection locking signal and what should be the strength of the injection locking signal. And you can see when we apply injection locking signal, all of them get locked one frequency, and we have a single resonance coming at 4.7 gigahertz. This was a trial. Now we're doing it at 35 gigahertz for a customer. So conclusions: accurate modeling of micro machine transmission lines carried out, theoretical and experimental investigation of large membrane circuits done, passive RF circuits demonstrated, several types of micro machine antennas, almost 20 types, with excellent match between theory and experiment demonstrated, 2x2, 8x8 antenna array demonstrated. In fact, we have done a production lot of 8x8. Active antenna concept demonstrated. Design of low loss switches and phase shifter done. In fact, I didn't, because of time, I am not showing you, because this itself is a lecture. And we have made 56 different designs of switches on gallium arsenide. And we are currently looking at packaging. These are being investigated. Thank you very much.